Hi, kids. Today we're going to talk about continuity, which is a word you're familiar with, but a definition you are probably not familiar with because it involves calculus. So, up until right this second, continuity to you has meant, can I draw the graph from left to right without picking up my pencil? And that's still a really good way to look at it visually. So we're gonna start there. So if I were to follow this graph left to right without picking up my pencil, I would follow along here and then I'd shoot down to negative infinity, have to pick up my pencil on the other side, have a hole here, down this way, pick up my pencil, pick up my pencil. So I have three discontinuities. And I put all three kinds in here because there are three kinds of discontinuities. So we're gonna start with that. There are three types of discontinuities, and you can read them on this visual that I have. And some of them you're familiar with, and some of them have names that you probably don't even know about. So this one is an asymptote, but it's also called an infinite discontinuity. And that should make some sense because asymptotes are when the graph on either side goes to an infinity, so it's an infinite discontinuity. This one here, yes, this is an open circle. It's not a hole. This is a jump because you have to jump from one function value to another. This one is a hole, as you're used to calling them, but they're also called removable discontinuities. I don't think there's another name for jump, but in this moment, I can't think of what it would be. So you have infinite discontinuities, removable discontinuities, and jumps. And you decide which one you have based off of which part of the limit or of the definition of continuity you fail. So I'm going to go through your definition of continuity now. We can talk about that. So your definition of continuity has three parts. So part one, we're talking about continuity at this value A. I'm going to call it x equals A. So continuity at a point. The first thing that has to happen is f of A has to exist. So your function value has to exist. So if I'm looking at this graph here, this jump is not discontinuous yet because it exists there. There's a closed circle. But this asymptote would fail the continuity definition, and the hole would fail the continuity definition because there's no other dot anywhere. The second part of your definition is that the limit of, as x approaches A exists. Okay, so the limit as x approaches A of your function exists. So again, for this one, for this visual, the infinite would fail here because you have one going to positive infinity and the other one going to negative infinity, and those don't match. The jump would fail here because your limit from the left is different than your limit from the right. But the hole would not fail because your left and right limits match. So maybe we need to write that too. Remember, for a limit to exist, the limit as you approach A from the left has to be the same as the limit as you approach A from the right. That's what it means for a limit to exist. And you might have questions where you have to set up two separate limits to make sure that they match. All right, the third thing that has to be true, so your function exists, your limit exists, those things have to be the same. So the limit as you approach A of your function has to be the same as your function value. So if I look here, none of these discontinuities are continuous, obviously. That's why I made it this way. The only one that's easy to show real quick, if I were to fill in this hole, and if I were to define this function again and say that f of 4 equals -1, if I had a different part, then I could fill in, I could remove that discontinuity by filling in that hole. So that's why all three of these conditions have to work. Okay, let me show you what questions look like for continuity. And we'll go from there. So here's the function. It's a piecewise. They're almost always piecewise functions. And we're going to go and force this to be continuous. So here's the first piece. And this is going to be for everywhere that x is not 1. And your second piece, I'm going to do this. X is 1. So this question is going to be asked a little bit backwards. And the question is to go find k so that f of x continues. So if they're going to ask you this, then the first thing you have to decide is where are you concerned about being discontinuous? And if I look at my piecewise, that should answer the question. This is where I should be concerned about x being discontinuous. I should be doing all of my analysis for when a equals 1. So because at 1, we switch from one function to another, and I need to make sure those match up. So the first part of continuity is that f of a has to exist. So I need f of 1 to exist. Well, if I read my piecewise, when x equals 1, this function is this weird k. Okay, well, that exists. I don't know what k is. That's the whole point to the question, but it exists at least. Let's go to part 2. Part 2 is that the limit approaches 1 has to exist. Now, here's where I'm going to have to do some work, because what this is saying to me is here's 1. I have some function going on here, and then at 1, where this value of k, so I'm going to call this k, and then I have the same function on the other end, doing whatever it is it's doing, whatever squiggle. So if I go to take the limit as we approach 1, I have to come from the left and from the right to make sure I'm getting the same value. So I'm going to split this into 2, and I'll just work 1 up here as x approaches 1 from the left, and as x approaches 1 from the right. The thing is, I'm on the same function, so this is repeated work, but I have to do it. So this is x squared minus 4x plus 3 over x minus 1, and the same function. You're on the same function for both the left and the right of 1. At least it ends up easy, because this factors as x minus 3, x minus 1, and I can reduce my x minus 1s. And then when I go to plug in, 1 minus 3 is negative 2, and this is going to do the same thing. So I get the same value whether I approach from the right or the left, which means that the limit exists, and that's so great. Part 3 of continuity is that what I got for 1 and 2 have to be the same. So I got k for 1 and negative 2 for 2, which means that k has to be negative 2. So if k equals negative 2, then this piecewise function is continuous everywhere. That's one way they can ask these questions, and there are a couple others. They're almost always in piecewise form. So just make sure you go through all 3 conditions for continuity. Every time you have a continuity question, you start with, does your function exist there? Does your limit exist there? And then are those 2 things equal? And then you should be okay to at least get things set up and started. But as always, please text me any questions you have. See you soon.